Good evening, everybody. Welcome to the fifth session of Exploring 3D Experience Works. My name is John Martorano, and I'm joined next to me is Gian. We are both industry process consultants currently located in Waltham,
Yes,
Massachusetts.
we are.
And of course, we are still divided by this thick wall here. So all COVID safe. But just a reminder for everybody, whether or not you've joined us before or you're joining us for the first time now, if you have questions or comments, use that chat because we'll be checking in periodically. And again, thank you both for joining. Thank you everyone for joining. And if you are new to this series, though, you may have a question. And what is this question? Well, what is 3D Experience Works? It's our growing portfolio of handpicked tools by Solidworks to tackle just about any product development challenge. So this is 3D Experience Works. And as you can see, we have different brands that tackle different phases along the product development process. So in its simplest form, it's planning, developing, and releasing a product. And we all know that SolidWorks tackles that second step just perfectly, really. So the rest of 3D Experience really fills in the gaps to provide that one-stop shop of all our connected solutions. And if you joined us in 2020, you know that we've been all over the map covering all of these different brands, and today's actually going to be no exception because we're doing something completely different that we haven't done this year so far. Isn't that right,
Oh,
Gian?
yeah. We're going to be covering a new brand that we did a little bit last year, but we're going to do a deeper dive today into some of the simulation products offered by the Simulia brand. So this brand does all types of crazy simulations, almost all of them built on the Abacus solver. So if you know anything about simulation, you probably know that that's a very powerful piece of technology behind the scenes. And today we're going to be focused on some of the cloud connected simulation products from Simulia that are a part of the 3D Experience Works portfolio. So I want to paint the picture that this is very, very wide in range. Like there are so many different things that you can do in simulation. We have structures, we have fluids, we have electromagnetics, we have plastic injection, and tools for collaboration and review. You know, there's so many different things that you can do with this. But today we brought on a couple special guests to show structures and fluids. So that's what we're going to focus on today. And to talk about those, we have Shreyas and Ramesh joining us to talk about structures and fluids today. So without any further ado, let's get you guys on screen. How's everybody doing today?
Hey
Welcome,
John, hey
guys.
Gian.
Hey, John, Gian, how are you guys doing? Good to be here.
Oh, great to have you.
Yeah, good to be here.
Great to have you. So Shreyas, you're our structures guy. Tell us a little bit about yourself, your background. What are we going to see today?
Yeah, absolutely. So today I'm going to show you some really interesting capabilities the 3D Experience platform has, and to be more specific, the structural mechanics engineer role on the 3D Experience platform. And the data set I'm working with today is one from a Formula SAE car, which is basically an impact attenuator assembly on a Formula SAE car. It's a front crash structure, so we are going to see that and see that in action, and then see some tips and tricks as far as structural mechanics engineer role is
Yeah,
concerned.
let's see it. So let's get right into it.
Yeah, absolutely. But before that, Gian, what I want to do is I want to give our audience a quick high-level overview of different structural solutions that we have on the 3D Experience platform. So the first one we have is called the structural designer role. Now, let's say you're a designer, you're an engineer who is interested in doing a linear static analysis or frequency or buckling analysis, even thermal analysis. Then probably structural designer role, that is our entry level offering, is best fit for you. Then we have another role called structural engineer role. Now, uh, if you want to evaluate, if you want to do a quick linear dynamic evaluation of your system, then probably structural engineer is the role you're looking for. Then we go on to some high-end things that these solutions can do. So the next role we have is the durability performance engineer, which really lets you do a lot of things. So let's say you are an engineer or an analyst who is working with complex materials, or you need some advanced meshing and contact definition techniques, or you're looking to set up a fatigue analysis, or even set up a nonlinear static analysis, then the durability performance engineer role is probably the one for you. And then we have our final offering, which is called the durability and mechanics engineer. This is our high-end offering. It comes with tools. It comes with features that will let you do a nonlinear dynamic analysis, and it also comes with a material calibration app that I am going to explain you in today's presentation. So yeah, that's our structures solutions on the platform. And if you're wondering if you want to know more about the pricing, or if you want to in general explore these roles further, I would highly encourage you guys to get in touch with one of our resellers, or what you can do after the presentation today is just visit our website, and the link is in the description below. So yeah, with that being said, let's move on to our today's presentation. So I want to give you guys a quick context about what Formula SA is. I'm sure it sparked some interest in some of our audience. You may be currently working on a similar project, or may have worked on a similar project in the past. So Formula SAE is basically an engineering design competition where students from all across the university come together to build a single-seater Formula style race car, which typically should look something like this that you see on the screen. So the challenge in these competition is it's really is, look, it's definitely a race car. You want it to be fast, but the main goal, or the goal apart from what the primary goal here is, to come up with an well organized, well engineered overall package, which is backed up by a robust financial and sales planning. So as I said, today I'm working with a data set which is called as an impact attenuator assembly on a Formula SAE car, and I would like to give you guys a quick preview of what it looks like. So we have a space frame chassis of a FSAE car, and then we have an impact attenuator assembly attached to the front of it. So what this really is, it is a crash structure that has to absorb a certain minimum amount of energy and decelerate the vehicle in a controlled manner. So the physics we are trying to simulate here is, we have the rigid barrier, we have the foam and the anti-intrusion plate that makes up the impact attenuator assembly. And then we have what we are going to do here is just crash this assembly into the rigid barrier at a speed of 7 meters per second. So that's the scenario we are or I am trying to demonstrate today through this presentation. So before we move further, what I want to show you guys is a quick visual roadmap of the 4 important things that we are going to cover through this presentation, which I'm really excited about. So Solidworks to 3DEXPERIENCE, how to transfer your model, how to transfer your assembly from Solidworks, which is your primary CAD tool, to the 3DEXPERIENCE platform. Then we'll take a quick dive and then look into how we can set up material from the test data that we have, how we can calibrate it using the material calibration app. And then I'm going to show you some interesting technologies that we have that will be useful for you guys to set up your model, set up the scenario, and then also show you some tips and tricks as far as post-processing our results are concerned. And then show you the workflow where we can go back to SolidWorks, make the design change we want based on the results that we got, and then come back to the platform again. So let's go ahead and start with our first important point that we want to see. So let's say you have an assembly in SolidWorks. Okay, in this case, we have an impact attenuator assembly, which also consists, which also comes with a rigid wall. So we have the foam, we have the anti-intrusion plate. So all I have to do is first make sure that we have the 3DEXPERIENCE add-in checked in. After that, it's really simple, guys. So what we have to do is just click on the assembly that I want to take to the platform, and then through the compass that is on the top left corner, all I have to do is select an appropriate app that I want to push my geometry to, and then yeah, that's about it. Once you're on the platform, you can start with setting up the physics simulation, giving it a name, create an analysis case. In this case, we'll go with a structural analysis case, and then yeah, let's quickly verify if we have everything on the platform. So we have our rigid barrier, we have the foam, and then we have the anti-intrusion plate as well. Okay, so once on the platform, you have the option to follow an assistant. Now, what is an assistant? So an assistant is basically an expert sitting right next to you. So assistant option or assistant panel on the 3DEXPERIENCE platform has very well laid out steps that will guide you through the entire workflow of setting up the simulation, simulating it, and doing some post-processing as well. So it is a tool that comes in very handy, especially if you are getting started with the platform, or in general, if you're new to FEA. Okay. So let's start off by assigning some materials, right? So the platform has a vast library of engineering materials. But remember, we are working with a material for a crushable foam. So for that, what I have is I have some test data. And then what I want you to see is how easy it is to get the test data into a material calibration app, calibrate it, create a new material, and then use that material in our simulation. So let's
Shreyas,
go ahead.
just quick question. When you're
Hey,
talking
Gian.
about your test data, are you talking about like from like an instron, like pulling like one of those dog bone samples, something like that?
Correct. And that's exactly what I'm going to show you right now, how we can get our data into the calibration app and then create a new material out of it. It's very interesting.
Yeah, let's see it. I'm looking forward to seeing some stress strain curves.
All right. So yeah, the material calibration app, you can basically access it through the compass and in the top left corner. So we will start off by naming our material, and we have a data for a crushable foam, right? So a typical data that we could have is it can be in Excel form, or it can be in text form. Both are supported. All you have to do is just bring it to the platform and then import it. So let's see how it's done. So a typical data for a crushable foam can be data from uniaxial compression test, or maybe a volumetric compression test. So what we see here on the screen is some data from the compression test. So all I have to do now here is just drag the data, select everything, bring it to the platform by clicking on import. Okay. So similarly, what we can do is we can bring in the volumetric compression data on the platform as well. So same thing, just drag it, click on next, and click on import to bring it to the platform. Okay. So now we have our data here on the platform. A couple of different options that we can play around with is in the material model window is we can specify the hardening type and then the number of stress strain pairs on the curve. So for simplicity, let's keep the stress strain curves, number of stress strain curves to 2 right now. And then the hardening type in this case is going to be volumetric.
Okay. Hey, Shreyas,
Okay.
another quick question for you.
Yeah, sure.
It looks like somebody was just wondering, is the assistant that you were talking about before, is that assistant similar to like the SolidWorks Express wizard? Sorry, Simulation Express wizard in SolidWorks.
Yeah, I think Ramesh will have a good idea about this. Why don't we bring in Ramesh to answer this? Ramesh?
Yeah, it's very similar, right? I mean, the Express tools are great, but it also has a step-by-step process of walking a user from start to finish, right? So it's the same concept, same workflow here with the assistant on the 3DEXPERIENCE platform. It does exactly the same thing. It's more elaborate, more options because you're doing a full-blown multi-physics or a high-scale nonlinear analysis. So but the workflow is exactly the
Okay.
same.
Hey,
Yeah,
while I have you both
right.
here, we just got another question wondering, so the data is imported in SI units, right? So that was the question, but I think the real question is, does it have to be in a certain unit to be imported?
No, not
No,
really.
so you can adjust that. That's good to know.
Yeah, yeah. You can adjust that to the calibration
Great.
app.
Great. All right.
Yeah,
Well,
yeah. And yeah, going back to the assistant question. Look, I have been using the platform. I just got started with the platform. It's like 3-4 months I have been using it, and it's a really good tool. It is so simple to get a good hold of, and it really helps you. It will take you through the entire workflow without any hassle.
cool. Yeah, let's see what's next to get these materials all calibrated and set up that model.
Yeah, sure. So yeah, all you have to do is click execute. The calibration app will run in the background. It will go ahead and calibrate the data that you brought in, and then create a new material out of the data. So the action bar or lets you just create a new material. You can go ahead and name it, give a description, and it is ready to be used in your current session. But the good thing here is you can save it to be used in your further future projects as well.
Yeah, makes sense.
Okay. Yeah. All right. So yeah, let's go ahead, send the material or the push the material to this current session, and then it's ready to be used. Okay. So the next thing what I want you guys to see is some really interesting meshing techniques that we have on the platform. So we have techniques such as beam meshing, surface meshing, a sweep 3D mesh, which you can see on the crushable foam. And what this basically helps you to define how these components are assembled. And uh, so we also have different mesh editing features. So to name a few would be translate, rotate, or extrude. So through this, what we can achieve is, or what we can do is, we can really transform and edit the mesh on a very local level. You can edit the nodes, you can edit the elements as well. So the next thing I want to show here is a really interesting property that we get it from Abacus. We get it directly from Abacus. So this is called the general contact property. It is a global interaction property, and is a very fast and efficient method for specifying contact behavior uh, between multiple components in your assembly, or let's say all components in your assembly. That's the range of the components that it can handle. So this property lets you define the default behavior of contacting surfaces during your simulation. So this is a really interesting technology that we have on the platform. So yeah, for the sake of today's presentation, I have already ran a simulation. So what I want to do right now is show you some really interesting results, and also show you some tips and tricks on how we can interpret those results. Okay. So yeah, a typical data we can analyze from a simulation like this, simulating a crash structure, is how the energy values look like. So what I have here is three different energy plots. So kinetic energy, plastic dissipation energy, and total energy balance. So the kinetic energy is represented by the blue curve, as you can see from the see on the screen, and the green curve represents the plastic dissipation energy. So as the crash progresses, the kinetic energy goes down and the plastic dissipation energy goes up. Which is, the plastic dissipation energy is basically the internal energy that is being absorbed by the crash structure as the assembly impacts the rigid barrier and then rebounds. So let's go ahead and quickly also take a look at how the velocity behaves, or what is the impact on the velocity as the crash takes place. So what I have here is the velocity plot, which you can see on the screen. It reduces gradually from, so we had a constant speed of 7 meters per second at the beginning, and as the crash takes place, as the structure gets plastically deformed, it reduces the speed to a certain minimum value. and then keeps it constant, which is basically represented by the rebound as you see on the screen. Okay. All right. So so now we are at a stage where we have some results, uh, and we are ready to analyze those. And through the results we just saw, let's say let's just assume that our design is probably overperforming a bit. So what I want to do now is I want to go back to SolidWorks, make some changes in my design that I think will probably make my assembly more in line with what our team goal is. So let me show you how simple the workflow is. Let me show you how the design changes are done. Okay, so so I go back to SolidWorks. What I have is my previous assembly here. I have the crushable foam. I have the anti-intrusion plate. Now, what I want to do is I want to reduce the size of my crushable foam. So, uh, and probably make some changes on the draft angle as well. Okay, so I have my revised iteration, which you see here on the screen, and then I did not do any changes on the rigid barrier or on the anti-intrusion plate. So all I have to do now is go to the connector, select the assembly, and basically follow the similar process and push it to the mechanical scenario app on the 3D Experience platform. And once you're on the platform, do a quick global refresh to update the individual components that you have made changes on, and there you go. You have your new geometry on the
Right.
platform.
Wow. So Shreyas, it's pretty easy
Yeah,
to replace by different revisions of a component as well, right?
correct. Yep. That is correct. It's pretty much the similar workflow that you'll have to follow that I just showed. And once you're back on the platform, do a quick global refresh to update your components or update your assembly
Cool.
links.
Yeah, I won't hold you up. Let's
Yeah.
see how the second results go.
Yep, absolutely. So uh, I have this second iteration simulated as well. So what I want to show you guys is a quick comparison between these two design iterations. So we had our first one, obviously. So the first one, you can see the plastic strain contour on the first iteration, and this is our second iteration. You can see some similar results on the second iteration as well. But what about the energy plots, right? Those are the main ones that we want to study. So let's go ahead and take a quick look at how the energy plot look like for both these iterations side by side. So uh, you can clearly see from the second iteration that it probably hasn't absorbed the amount of energy that it was supposed to be. So you can there's really no limit on the number of iterations that you can do, but yeah, it again depends on how much or what time constraint are you working in. So just for the sake of today's presentation, just for the proof of concept, I came up with two iterations, and then we have the comparison side by
Yeah,
side.
I
So
like your comparison
yeah,
here, and
yeah,
so it looks like the curves. So the orange one is like the total kinetic energy you said, and green is the absorption through the foam. So
correct,
yeah, it looks like it
correct.
barely absorbs like maybe 25% of it or so, and then the rest of the kinetic energy doesn't never reaches the bottom. So the rest of that would be absorbed by like the frame, right?
You.
Yeah, and that's
Probably
that's
not good.
that that's a really interesting, yeah, that's a really interesting observation, Gian, and that is exactly what I'm going to show you next. How scary it looks like when you try and simulate or try and simulate the entire structure with the chassis. You can see the stresses and deformation transferring on the frame as well. So look, I don't know about you, Gian, but I definitely don't want to be a driver when this
Yeah,
happens.
that's a hard pass for me as well.
Ouch.
Such a cool
Yeah.
animation though.
All right.
That's so cool.
Yeah.
Okay. So yeah, that's it, folks. That's it from my side. But before I hand it back to Gian, I want to show our audience some high-end capabilities, high-end scenarios that we can solve using the structures solutions on the 3D Experience platform. So yeah, just want to quickly check with you, Gian, if we have any questions from our audience, or yeah, it's just want to hand it back to you again.
Yeah, I think we have one question saying, this is cool. How can I be a simulation engineer? So kind of a
Yeah,
broad
so
question, but what do you think, Shreyas?
Well, definitely. You must have a lot of interest in simulation to start off with, but then again, we also have different products, different structure solutions. So if structures is something that you are interested in, you can probably get started with using one of our tools, or there's also something really interesting coming up your way. Just want to give you a quick teaser that's about CFD, computational fluid dynamics. So if you are interested in that, just stay tuned, and then you'll get to know some really interesting things about that.
Yeah, yeah, I'm excited.
Can't wait.
Yeah, I know.
Yeah.
John, you're excited. For those of you who don't know, John's a pilot, so you must live for this stuff,
Oh
huh?
wow.
Yeah, I'm hoping to see at least, one aerodynamic example here. I don't know, but
Yeah, it's coming your way, John.
I know. I'm so impatient.
Hey, let's get Ramesh back on there. How you doing, Ramesh? Ready to...
Hey, good. How are you guys? That is really excellent, Shreyas. Just looking at the crash test. But yeah, I'm a daredevil, so I would like to sit in the chassis when the impact happens, right? So, but no kidding. So, hey, so what I was able to do, guys, is really pull while Shreyas is doing the simulations. I know I was able to actually pull his lightweight version of the simulation results and use an app on the 3D Experience platform, which is called the Physics Simulation Review. So this is a really cool app that you can use to share results, look at animations like the ones that's shown on the screen. And it's a nice way to share information, communicate analysis results with someone who might be part of the project, but might be sitting miles away from you, right? So all you need is an internet connection and a browser, and you're all set. I can do this from anywhere, anytime, any place. Okay, so I can even do some markups.
No
like
downloads or anything?
No downloads, zero download, right? So think about this is like your Solidworks e-drawings tool, guys. So and I think it's a little bit more powerful because of the fact that you can do analysis animations, which is really great. But it's a lightweight version. I don't want to open up Shreya's entire simulation, right? I just want to investigate what he has done. I might be just a key stakeholder, but I can just review what he has done and make do some annotations, markings, a nice way to kind of share information back with my team.
Awesome.
Yeah. Well, I'm excited to see some fluids, but it looks like we did just get one question that I think you probably know the answer to, Ramesh. Somebody was asking if you can use 3D Experience with the education version of SolidWorks.
Good question. I'm not 100% sure, but we can certainly get back to that a person offline. Let me do a little bit more research, unless
yeah, I think our friends on the back end might be able to find us the answer quick, so we'll come back to that one. But yeah,
okay, perfect. Okay, all right, guys. So let's dive into fluid dynamics engineer on the 3D Experience platform. So I'm going to show you some computational fluid dynamics. You saw Shreyas in action showing you the structure side of things, but computational fluid dynamics, it's different physics, but it's also equally important to analyze, what the aerodynamic performance of a Formula SAE race car looks like, right? So that's exactly what I'm going to show you. So a quick agenda, right? I want to give you a quick, like a little background of different fluid solutions from Simulia. Then we're going to talk about fluid dynamics engineer technology, dive straight into this aerodynamics example, look at what the tool can actually help us with, and finally wrap it up and have a quick call to action for folks in the audience today. All right, so background is very simple. I'm just going to list out some solutions. So today we're going to actually go and look at fluid dynamics engineer, right? So that's we're going to take a deep dive on this particular tool or role on the 3DEXPERIENCE platform. So this is very CAD-centric, and I call it as mainstream analysis because anybody technical can use this tool. All right. Next up is actually plastics injection engineer. It's a little bit different type of CFD physics, I would say. But imagine like if you're designing plastic parts, doing mold designs, so those plastic parts are manufactured through an injection molding process. This is a great tool to be able to identify, reduce, and fix manufacturability issues early on in the design process. And then we have some very advanced, very high-level multi-physics, multi-scale type of CFD tools like XFlow, which is based on lattice-Boltzmann technology. So fluid dynamics engineering is based on the RANS technology. So both these technologies are actually very popular in the CFD industry today. But so XFlow is more for very high frequency, high transient fidelity applications. Think about water splashing, right? So you can use XFlow to simulate those scenarios. But also we are looking at multi-phase, moving geometry, fluid structure interactions. XFlow is a very powerful tool to look at. Then we have PowerFlow, which is using the same lattice-Boltzmann technology, but it's again a very niche, I would say, highly customizable application that can actually help solve a very specific problem within an industry, such as aerodynamics, aeroacoustics, or aerothermal. Okay. Today, so with all of these tools, keep in mind, we can definitely help you out, whether you are in transportation and mobility industry or aerospace, defense, high tech, and so on. We have the simulation solutions definitely can help you out solve your engineering challenges. All right. So let's go ahead and focus on the mainstream CFD, fluid dynamics engineer role. I'm going to talk a little bit about the technology, give you a 30,000-foot overview of some of the key technologies. So let's start with the type of physics it can solve, right? So it does have a broad physics coverage, and keep in mind this is CAD-centric. As well, but you can see in terms of physics, just like any other CFD tool out there, there's so much of different levels of physics you can solve with fluid dynamics engineering, including multi-phase flows with surface tension effects, and even rigid body motion, whether it's driven or prescribed, just like the video that you're seeing here on the bottom, showing a tank which is being rotated about an axis, but the water inside is sloshing all inside the tank, right? So that's actually some high-level physics we can solve with fluid dynamics engineer. When it comes to turbulence modeling, we use a RANS-based turbulence model in fluid dynamics engineer. There are several turbulence models that are actually supported, such as the Spalart Almaraz. Then we have some advanced models like realizable K epsilon and SST K omega. And all of these actually use also the intelligent near wall modeling that is basically a hybrid wall function approach. So depending upon the coarseness and the boundary layer, there are several algorithms are used by the solver to give us the accuracy and the confidence in the results that we are after. And finally, meshing. So meshing, again, like I said before, this tool is CAD-centric, right? So there's a lot of automation that's provided behind the scenes, but you can also take a deep dive into meshing if you have to. But in terms of automation, right, it automatically extracts the fluid volume. It automatically heals bad geometry. It automatically closes any open surface that you might have, so that you're ready to actually start doing your simulations rather than trying to wrestle with the mesh, right? So when a fluid dynamics engineer uses hex dominant meshing, which is a body fitted mesh, and it also comes along with mesh morphing, which is really cool, a cool technology to use for simulating rigid body motions. Like the animation that you're seeing here is just an object floating on water. It's a free surface flow, but you also have, you can analyze the rigid body motion using a mesh morphing technology. All right. So let's take a dive into the aerodynamics example for today. So I got this formula as a geometry, race car geometry from Shreyas. And like any other CFD analysis, I want to start off very in a very basic, laid on the foundation. So I want to simulate 50 miles per hour. This thing is going at 50 miles per hour. So I want to simulate that effect and understand the physics. So the way you can be successful at simulation is really focus on the critical parts of your assembly, right? So what I call as a crawl, walk, and run approach. So in this case, we just want to focus on, let's say, the front wing and the rear wing, and also, we want to have that an idea of what's happening in the entire body, right? But let's say we want to focus on these two entities, and what do we want to understand? It's aerodynamics, so it's very, it's very obvious that we want to look at drag forces, we want to look at lift forces, and so on. Now, what I want to highlight, though, is how do we get started? Shreyas actually showed you, talked a little bit about the assistant. It's literally like an expert sitting right next to you. Same workflow exists here on the fluid dynamics engineer side, right? So we have the assistant, and this is why is it so powerful, right? Because it's a huge productivity tool that if you're new to using the tools in the platform, the assistant can actually help you with getting you started from day one or day two like that, right? So I want to give you a quick preview though into how this works. I'm not going to bore you with all the steps of this assistant, but just give you a quick highlight. So for example, I'm creating what is called as a fluid domain. And all I'm doing here is, I'm telling what geometry I want to include in my CFD analysis, as simple as that, okay? And then this is an external aerodynamic application. So I'm going to create a bounding box, which is really the volume of space around the geometry I want to capture. And here's some actually, all I need to do is input some numbers. And
so Ramesh,
basically
how do you define the box? Like, how do you know how big to make it, and like what exactly are you trying to capture?
That's great. So yeah, so when you're analyzing external aerodynamic problems like this, usually, a lot of the physics of the action takes place downstream of the geometry of the object, right? So you want to capture that downstream effect. So in the direction of the airflow, you can see you have a larger length, and that's typically, as a thumb rule to start, you can use 10 to 15 times the characteristic length of the geometry. Okay, so that's where, for example, you want to capture the wake region as much as possible. But the wake region can also, have a vertical height, right? A vertical direction. So typically in the vertical direction, we want to capture at least 5 to 10 times the characteristic length of the vehicle. Okay, so that's a starting point, a guideline, but really depends on what physics and how much of that physics you're trying to capture.
Great.
Good question. So what I want you to know is, in this particular model, we have 13 million elements. Okay, but I want you to walk away with looking at, not right now, but just at the end of this presentation, keep this in mind that when it comes to meshing the boundary layers, it is a super, super easy step. So for example, you can say, hey, here is my first layer thickness, and here's my number of layers. That's it. The program takes care of the rest, right? So making it easy, all the cranking is done by the software behind the scenes, but on the front end as a user, this is super easy for me to do. So just a couple of snapshots I took to show you how the meshing looks like. You can see the boundary layer meshing, how dense it is on the surfaces. And around the helmet. The helmet is not so interesting, right? But it apparently happened to become a part of the analysis. This is another screenshot showing you on the rear wing what that boundary layer meshing looks like. Okay. All right. So we have 13 million elements. What do you guys think? How long did it take to run this analysis?
A day?
At least 12 hours, I would say.
12 hours, yeah.
Yep. Yeah, back in the day when I was, if I was solving such a problem, maybe it would have taken me days and weeks. But yeah, I mean, nowadays, that's the beauty, right? Today, we are living in different times. We have the hardware infrastructure, and we also have access, we have the option to use the scalability of what the 3DEXPERIENCE platform cloud offers, right? So what I did was I just pushed this to the cloud and said, hey, just go ahead and solve this on the cloud. And so it only took about 37 minutes. So it used 144 cores on the cloud, and it came back in 37 minutes to give me the result I want. So this is a massive large scale problem that I can just leverage the power of the 3DEXPERIENCE platform cloud to solve the problems as fast as possible. And this is just one problem I'm solving. Imagine, and when it comes to simulation, right, you're not going to take one design, one scenario, run it, and you're done, right? You want to test multiple what if scenarios, right? What if I change the geometry? What if I change the wind speed? What if I change, let's say, the yaw angle? So there could be a lot of these parameters you want to analyze and get more data points end of the day, right? Because the more information you're getting early on in the design process, you're understanding what your product is going to do in real life in terms of its actual performance, right? And that's only going to help you, end of the day, make some good informed design decisions. Okay. But imagine this time, guys. I mean, 37 minutes, can't beat that.
Yeah, we even got some comments coming in from the chat saying, "No way, that's incredible." Yeah, it's tough to believe.
Yeah,
but
I didn't make. I absolutely, I didn't make this up. This is the runtime, wall clock time. I catch it from the analysis, but it is immensely powerful because of the fact that it's not just the number of cores, guys, but also think about on the cloud, you have access to a huge amount of memory, which the solver requires, right? You can always, if you have the hardware infrastructure in-house, yeah, you can mimic the same performance level on your local machines or local hardware. So what you're seeing here, guys, is really cool, right? I mean, so these are tools, Fluid Dynamics Engineer on the post-processing side. You can create some really cool graphics, rich visualization, where you can not only just look at results like a cut section of pressure or velocity or whatnot, but you can just superimpose the background the background image. You can even impart motion to the vehicle and create some really, really cool, realistic visualization videos like this. It's nice to share something like this with your clients, with your customers. It's not just a static image that you're sending across, but you're giving them a more real picture, a more three-dimensional picture of what's going on. So you can really use the tools on the platform to do that. So yeah, looking at cool pictures, pretty colors is good, but the question is, what data can I get out of the tool? Right? How do I make my engineering decision? What do I make sense out of these contour plots, for example, right? So let's take a look at it one by one. So on the front wing and the rear wing, I measured the drag forces and the down forces and got the efficiency, the L/D ratio to see if that's acceptable or not. That looks pretty good to me. But let's take a moment to look at some of the results here. So for example, what you're looking at is the turbulent kinetic energy. So these gray areas, right, that you're looking at is basically where all the high turbulent energy exists, right? And that is indicative of low pressure, or rather more, I would say, recirculation area. So this can actually give us some good insight into, is that acceptable? And a lot of times, and not in maybe Formula SAE, right? But in race car, other race car competitions, this low pressure region could be taken advantage of by the driver and the vehicle behind this car, right? So I'm sure all you guys know about drafting. So there's a low pressure region, so they can take advantage of. You always see that they tailgate the front car, and then this low pressure region gives them a little bit boost, and then they actually go to the side and overtake the vehicle in front of them. So very cool stuff, right? Cool. So there's a lot of information you can get out of this plot. But what I want to focus on is a very, very powerful result, which is called as coefficient of pressure. So there is an equation that's driving what this coefficient of pressure looks like. You don't have to memorize the equation.
Think
about this as a dynamic pressure. Okay. Why is this important, right? Well, you can really hone in and focus on, use the result here to actually improve the aerodynamic performance, improve the aerodynamic shapes on your vehicle. Let's take a look. So let's say, for example, right now I'm looking at the pressure and in the system. But what I can do now is create a coefficient of pressure value that's driven by an equation. So in Fluid Dynamics Engineer, I can just go and say, hey, look, I want to input half rho v squared, put in the equation times the pressure drop, the pressure difference. I can do that very quickly. And once I build in that equation, I can go in and create a new result plot. So I'm going to go ahead and select my coefficient of pressure plot, and I want to actually start by looking at what that looks, what it means on the surface of the vehicle. All right.
So we're going to look at like the high pressure or the low pressure?
Both. We're going to look at both.
Oh,
So if you look at the numbers, right, what this chart shows is a number going from +1 to all the way to -3.53. So +1 is really all the high pressure points or the stagnation pressure points. So, but if you look at, how does that help us, right? If you look at the top surface of the front wing as well as the rear wing, you can see all the red there. That's really good. We have a high pressure region, and obviously that makes sense, right? Because we want there's a low pressure region underneath this design, and so that actually provides that downward force that we are after. Okay. We can also try to look at this in a different way. So let's say, for example, I want to scale this to just show me the high pressure points, okay? Really where the air is just going to slam against the surface and come to, let's say, almost a complete stop, okay? So right at the bat, I can notice that I see a red spot on the very front of this race car. So what can I do about it, right? So I know that air is just stagnating there. Maybe I can change, it's a flat elliptical area. And let's say, for example, I can make it more pointy, right? And I can try to alleviate that pressure point. But if I try to do that, what's going to happen? Shreyas is probably going to shout at me and say, hey, look, you can't do that because I want my anti-intrusion plate and my crushable foam there. So the design is there for a reason. So I know at this point, yeah, even though we are seeing a high pressure point, I cannot mess around with this design in this area. So let's take a look at, maybe some other areas of interest. So let's say, for example, we are looking at the wheel area. So there's a spot there, but in reality, that spot is going to be somewhere lower. We're not going to see that spot right in the middle as shown here because I've not included any rotational effects on the car. But what I want to know is, for example, on these leading edges, what the pressure points are. That's as expected. But what I want to know is there a free flow of air over the wings, over the tires, into the center wing where my mouse pointer is? Because that's where, let's say, the radiator is sitting. And I want all the air to be actually coming in free flow through the radiator so that it can cool the engine sitting inside. Now, if I see a pressure point in those areas, somewhere in the center wing area, that's really a bad design, right? Because that only means that I'm not going to have sufficient airflow reaching my engine. And so what's going to happen? The engine is going to burn out pretty quickly. So that's kind of the design decisions you can make by looking at this particular coefficient of pressure plot, but utilizing the feedback we are getting from the software to make those design decisions. All right, so here we got some leading edges that are stagnation pressure points on the back wing. So it's really cool stuff, guys. I mean, it's not just pretty colors, but making sense out of those pretty pictures is really, really important. And so that's exactly what fluid dynamics engineer does. Right. So next, what I can do is I can look at this in a different way. So I can actually plot all the negative pressures, negative values of the coefficient of pressure. That'll actually show me the entire wake, just like that. Okay. So so you can see how tall that wake is, how wide that wake is. But here now I can say, okay, is that acceptable? Can I make the wake a little bit smaller? Reduce recirculation areas behind the vehicle. Maybe I want to change the angle of attack of these inverted airfoils on the rear wing. So I can play around with some design options there to see how that affects the overall physics of the problem. So lastly, what I want to do is I want to show you what's happening on the front end side. So this is looking at the velocity, and you can see the velocity underneath the front wing accelerates like crazy. It's just screaming in terms of the velocity, but it's almost like a Venturi effect that you're having on the underside of the car, right? So if you think about the Bernoulli's principle again, right? Higher velocity, low pressure. So you have, basically that's exactly what we want. We have a downward force that'll keep the car on the ground. But it's very important to also understand what's happening underneath the vehicle and so on. So next, what do I try? Well, I can just go ahead and look at the effect of changing some design variables like yaw angle, ground speed, angle of attack. There's so much we can do here, right? Literally. And the good news is when we are trying all of these in the context of a virtual simulation environment on the 3D Experience platform. And so it is only going to help us more data points and understand what's going on in the product. So
Ramesh, changing that yaw angle, is that just like a turn when the car is turning?
Yeah, that's a
About the
great
vertical axis?
Yep. It is actually simulating a cornering situation, right? So maybe plus or minus 15 degrees. I want to see how that affects the performance of my vehicle. But what's really cool is because I want to test multiple scenarios, I don't want to do it one by one, right? That becomes a little bit tedious and it's boring. But I can really take advantage of parameters on the 3D Experience platform. So I can create parameters for my yaw angle, for my vehicle speed, for my design, whatnot, whatever we are trying to do. Then we analyze that in the context of let it run through those parameters on its own and give us the final set of data that are for all of those design candidates. So what I've done is I've just summarized, for example, on the front wing, what's the effect of changing the yaw angle for two different speeds, 50 miles per hour, 30 miles per hour, and how does that affect my drag forces and my lift forces, right? So I want to bring in Shreyas. Shreyas, you're the expert on this, right? I mean, what do you think about these numbers? Do they look reasonable to you, or what do you think?
Hey, Ramesh. Yeah, I think these numbers make perfect sense to me. Some really good numbers you're getting there.
Perfect.
Definitely see the drag forces going up as the car accelerates. So that's good. You can see the difference there. So some parasite drag.
Yeah, it's very obvious. And then on the drag force here, we see a dip on the plus or minus 15 degree angle. That could be because of the frontal area. Now it's a reduced area that's facing the direction of the wind or the air. And maybe we see that dip a little bit, but we see a lift force is more or less consistent, just telling us that the design is pretty good, actually. So I did the same thing on the rear wing, guys. So same proof of concept. We see the same trend in terms of the drag forces and the lift force or the downward forces. So this looks pretty good. Okay, guys. So that is, I know, hopefully that is a lot of information. I know, but hopefully it resonated with with the audience today. But let's wrap it up in the interest of time. Just to recap, you saw the structures roles, you saw the CFD, the fluid dynamics engineer role today, and both these roles on the 3D Experience platform really have been created and keeping the designer in mind. So that's why I keep iterating, like it's CAD centric. It's it's actually talks to your SolidWorks environment, so you can push design changes and analyze multiple what if scenarios on your designs very quickly. You saw the technology both on the structure side as well as on the CFD or the fluid side. Integration side that Shreyas showed how it's pushing a different design of the crushable foam from SolidWorks into the platform to do a new simulation. And then collaboration, right? So in the beginning of my presentation, I was poking around when Gian said, hey, Ramesh, just get started. I was poking around investigating what Shreyas had actually done. So the collaboration is really huge here, guys. I mean, I can work, now in a single environment instead of working in silos, right? If I want to share results, if I want to actually do some investigation into my team's project, I can just simply pull data from the 3D Experience platform and work, do some markups and send it back to my team for review. So there's a lot of collaboration that you can do on the 3D Experience platform. You saw the scalability side of things. That's huge. I mean, solving a 14 million element problem and in 37 minutes, that's really remarkable, right? I mean, and there are problems where typically you need 40 million elements or 60 million elements to represent your aerodynamic boundary layer. So imagine those kind of problems. Now you have the power of the 3D Experience platform to exactly, to run those problems like super fast. Then we saw the productivity side of things. So that's basically your assistant. There are tools to actually help you get started, because we know when you're new to CFD or structures, you want a quick way to get things started. So the assistant is a great way of looking at, how productive you can be with the tools. And finally, the on cloud, which is really, showing the power and the scalability of whether if you have hardware infrastructure in-house, or if you don't have that, no worries. Or if you have a mission initiative, your company wants to, reduce the hardware infrastructure, IT infrastructure, we do have an option to actually where you can actually solve all your problems in the cloud. So with that, I'm just going to I just have a quick call to action, but I'm going to hand it back to Gian. But if you have a QR code reader on your phones, feel free to take a picture of this QR code. If you want to learn more about structures and fluid to fluids solutions, you can go to solidworks.com/domain/simulation and learn more about our solutions, or contact your local SolidWorks reseller for information regarding the tools. All right, so with that, I think I'm done. Gian and John, it's back to you guys. Thanks everyone for your time, and have a great day.
Thank you, Ramesh.
Yeah, I mean, thank you both so much. Just I'm really amazed at how much you're able to see. I mean, air is an invisible fluid, and to be able to visualize it like that is just it's truly valuable. And then also same thing with Shreyas. I mean, your crash test, it happened so quickly. There's no way that anybody could actually visualize that in their mind. So I think that's amazing, the insights you can get from the data in like such a short amount of time.
Yeah. Hey, John, quick question for you. I think did we get an answer about the education options for 3D experience for students?
So we have 3D Experience Works for students and educators, and you can learn more at edu.3ds.com. So that is easy enough link to remember, I think, and maybe Sarah, somebody can throw it in the chat.
I think she already did, and we
Oh,
we got a lot of great feedback. People saying, Ivan says that this is amazing. Actually, he's wondering if there'll be a recording of this somewhere. And the best part of us being on YouTube Live is you're already there. So you can bookmark this or take the URL, grab that share link, and you can actually take the little slider and scroll back to the beginning and watch it over right now if you really wanted to. So thank you again, everyone, so much for joining. A lot of great questions and amazing material. I'm always amazed by what we're able to do with simulation. And as always, if you liked what you saw, you want to learn more, check out those links in the description, like Ramesh and Shreyas were saying. And I want to give a big, huge thank you to you, Ramesh and Shreyas, but another big thank you to Sarah, Michael, and Sashi, who are helping us out on the back end today and making sure the stream runs smoothly and all of everyone's questions got answered. So if you liked what you saw,
yeah. Thanks, Gian and John. Real quick, I think we couldn't have done this without you. So thanks for having us today.
Thank you guys.
Thanks, Gian.
Thanks for joining.
Sean.
I mean, we love the simulation, but we are nowhere experts the way you guys are.
Yeah.
But if you liked what you saw today and you want to join us for the next session, it's actually going to be on June 24th. So once again, same time in 4 weeks from today. And Brian Zayas is going to be joining us to go over some project management, some lean team features of the 3D Experience platform, how to run your team more smoothly, more efficiently. I'm really excited to see that one. But yeah, until then, like, share, and subscribe as always if you liked it, and hit that little bell notification if you want to be notified of our next videos or live streams that get posted. Oh, almost forgot. For those of you who know of our cadence, kind of our every Thursday, we have a new live stream that's either us for exploring 3D Experience Works, it's SolidWorks Live, and it's SolidWorks Live Design. So next time we actually have Jan Killy, who's going to be showing some 2D functionality with DraftSite in next Thursday, same time this next Thursday. He'll be showing that on SolidWorks Live Design, hosted by Brad Williamson. So definitely go check that out. And yeah, thanks again for joining, everybody. Until next time.